Welcome back to the channel. Today's mini lecture will continue with the Earth processes, focusing on atmospheric and oceanic circulation, as well as weather and climate. Well, let's get started. So in terms of atmospheric circulation, remember in a previous lecture we spoke about the angle of incidence, the angle of the sunlight striking the surface of the Earth. Depending on that angle will depend upon how much light, how much heat, how much energy is delivered to the surface. In this case, the atmospheric circulation is caused by the differences in the temperature, again due to the variations in the amount of solar energy, the angle of incidence. When you have sunlight striking the surface, you have heating. The heating then causes the air to warm, which makes it less dense. The warm air rises. As it rises, it cools. As it cools, it becomes more dense, which causes it to descend. And so you start setting up these convection cells that have warm air rising, cool air descending. Now, when we're talking about surface winds, that isn't necessarily a heat function, that is more an atmospheric pressure function and the Earth's rotation itself. Remember, wind always will blow from a high pressure system to a low pressure system. Now, these convection cells that I spoke about, again determined by the angle of incidence, the sun's rays striking the surface of the Earth, depending upon the tilt, will set up these Hadley cells, these convection cells that can be found in a very uniform pattern across the surface of the Earth. Starting at the equator going north, you have heat delivered at the equator. The heat then rises. You have condensation because the warm air is rising. You have tropical then rainforests because of the rainfall. But then just further north of that, all of that air has been wrung out, and you have air that's now descending, which makes it dry air. Therefore, you have deserts. The convection cell is then repeated over and over again, north and south of the equator. Now, in terms of prevailing winds, remember those would be surface winds that are present pretty much most of the time. Those are based upon the Coriolis effect. The Coriolis effect is caused because the Earth is rotating. The Earth is a globe. Because the Earth is a globe, the equator is spinning faster or moving at a faster rate than the poles. The atmosphere is drug along behind it, just a little bit of a lag. And so you have this pulling motion on the atmosphere, which causes winds, especially there towards the equator. You have the southeast and northeast trades. Then further north of that and south of those, you have the westerlies. But those are your prevailing winds, again, caused by a rotating Earth, the Coriolis effect. The winds that we get on a day-to-day basis, those would be caused again from high pressure system equalizing to low pressure system. Now, just like the atmosphere, the ocean also has density-driven circulation. That is what is driving the ocean currents. These large circular patterns, a conveyor belt of heat transfer, all driven by density. The warmer water is at the top. You have that moving at a much higher speed. As it begins to cool, as it moves north and south of the equator, it becomes more dense, which forces it down, causing that rotation. This conveyor belt of heat and energy transfer throughout all of the Earth's oceans is also known as the thermohaline circulation pattern. Thermo meaning heat, haline meaning salt. Again, the salt and temperature really determine the density and which direction that water is going to be moving. The conveyor belt is also very much responsible for nutrient cycling throughout the oceans, as well as oxygen cycling. Remember, what sits at the base of the ocean food web? The plankton. The plankton rely on this conveyor belt. So now that you've taken a closer look at both atmospheric and oceanic circulation, I want you to start thinking about how do these big conveyor belts, both in the atmosphere and in the ocean, transfer heat? What is the result of that transfer? How does the physical location affect what the overall weather and climate over a long term will be. So let's take a closer look at climate and weather. So now that we've addressed atmospheric circulation and ocean circulation, these are the main influencers again on climate. Climate is a long-term average. This is not day to day, year to year, or even decade to decade. This is long-term. These are based on patterns collected over long periods of time. And if you look at this climate chart here displayed on the screen, this is Earth's climate from basically inception to today. We use climagraphs to illustrate the average temperatures, precipitations. These are all graphical representations that allow us to visually see the results rather than just trying to interpret numbers. Now, when we move into weather, weather is short term, day to day, hour to hour, even minute to minute in some cases. Again, this is displayed on climate graphs. You will see this would indicate the seasonal precipitation levels here in California in the West. You can also look at the overall precipitation forecast. Now we're talking a 7-day. And although it is true 7 days is longer than hour to hour or minute by minute, this does not make it climate. You'll notice on this graphic, it actually displays the various different weather conditions all displayed via their own color. This makes it very easy to quickly gauge what the upcoming weather would be. So to keep things really clear, weather and climate, the conditions in the atmosphere at a given place and time, temperature, pressure, precipitation, how much clouds are in the sky, what is the relative humidity, wind, wind speed, wind direction. When we come to climate, that is a whole nother story. This is long-term averages, averaged out well over time, looking at patterns that exist. Remember, it is the long-term weather patterns that determine climate. Again, the two biggest factors, temperature and precipitation. So now that we've looked at weather a little bit, let's go ahead and take a look at the primary influences of that weather, the actual engine behind it. So we have in North America exposure to all four of the air mass types. Again, these are based on two characteristics, temperature and humidity. So if it is dry, it is always going to be continental. If it is wet, it will always be maritime. If it is warm, it will always be tropical. If it is cold, it will always be polar. So you'll see these big air masses that move across the United States, move across North America, again, pushed by the Coriolis effect and those prevailing winds we talked about. When these air masses bump into each other, that is when we have interaction. That is when we get fronts and storms, and in some cases, cyclonic storms, storms that rotate. And as these air masses move across the landscape, they will run into landscape features such as mountains. And this is another method in which precipitation is delivered, one here in the valley which we are very familiar with, the orographic effect or the rain shadow. What happens is you have heating that causes the warm air to rise, taking moisture with it. That air mass wants to continue its path. However, the mountain is in the way. So the air mass has to rise above the mountain, and the only way it can rise is if it loses its moisture. And so you have your precipitation on the windward side or the windward slope of the mountain, and then the rain shadow side is always going to be dry, and in most cases you will find a very dry area. Here in the valley, we are affected by the San Gabriels to the west of us, but if you go further to the east, you run into Death Valley. Now we get to El Nino. This is actually the warming of the surface waters of the Pacific Ocean, and this causes changes in the overall climate and precipitation patterns. The opposite of the El Nino effect is La Nina. That happens again as a cycle, and that is the cooling of those areas in the Pacific. Both of these events affect climate, and weather. Now, we talked about that interaction, those cyclonic storms. Now, a cyclone, again, is always going to be rotation in the northern hemisphere. Cyclonic storms always rotate in a counterclockwise motion. However, in the southern hemisphere, they will rotate in a clockwise motion. The easiest identifiable cyclonic storms would be hurricanes, and we are coming into hurricane season right now. Another example of a cyclonic storm would be a tornado. This is a condensed, small version of a cyclonic storm. Again, a rotating funnel of air. This is caused when you have a major collision between masses of cold, dry air interacting with warm, tropical, moist air. In terms of wind speeds, tornadoes can have wind speeds up to 300 miles an hour, but again, that is extremely condensed, whereas a hurricane will have sustained wind speeds of up to 175 miles an hour. Whereas a tornado will come and go in minutes, a hurricane can last for hours of that sustained wind, in addition to all of the precipitation that is delivered and the pushing of the ocean ashore, the actual storm surge. That concludes our mini lecture on atmospheric and oceanic circulation, climate, and weather. Hopefully, this was able to give you a little bit more knowledge on how this balancing act that's going on between the ocean and the atmosphere and the land, and how that interaction between heat transfer and precipitation transfer affects weather and climate, long-term climate, and how those then affect life and how adaptable life is in those environments. As always, if you have any further questions, don't hesitate to place those in the comment section, and stay safe, stay home, and wash your hands.